So I want to talk to you in this lecture about Ampere's law. So Ampere was a French physicist who discovered a very nice relationship that employs a high degree of symmetry and symmetrical thinking for finding the magnetic field due to a current distribution. So we're going to use what we already knew from previous lectures in the Biot-Savart law to walk us through the reasoning that we're going to use in Ampere's law. So if you don't remember that, please go back and watch the other lecture on the Biot-Savart law first. All right? Here we go. So we already know from the Biot-Savart law that the magnetic field for a long straight wire makes circles around the wire. The direction that the circles are made by the magnetic field is given by our little alternative right-hand rule. So here I show a long straight current carrying wire with a current pointing upwards. So it flows like this. So if you take your right hand and you point your thumb in the direction of the current, then remember that the magnetic field is going to encircle that current carrying wire in the direction that the fingers of your right hand naturally curl. Don't bend your fingers the wrong way, okay? In the direction they naturally curl, okay? So what this would mean is that if I look top down on my hand, that the magnetic field makes loops around the wire in a counterclockwise direction, okay? So Ampere noticed that there was a high degree of symmetry here, and that if you did a line integral of the magnetic field in a closed loop around that wire, in other words here mathematically expressed as the integral around a closed loop of B dot ds, okay, then you got mu naught, the permeability of free space, which is 4 pi times 10 to the minus 7 Teslas meters per amps, right? That constant mu naught times the current that was enclosed by that loop, okay? So sometimes we call these loops Amperian loops, okay? Just like we called for electrostatics Gaussian surfaces. This is kind of the same sort of logic that we would use for a Gaussian surface, okay? Now, Ampere's law describes the creation of magnetic fields by all continuous current configurations. So it's always true, but just like Gauss's law, it's not always useful. It's most useful for this course for analytical solutions if the current distributions have a high degree of symmetry. So loops are great, long straight wires are great, solenoids perfect, toroids good. Anything with a high degree of symmetry, you can easily use Ampere's law to calculate. If the symmetry gets broken, if it's more complex, you might need to numerically integrate it in order to get things to work out. Okay? Now you might be asking yourself, well, which way do I do these line integrals, right? Which way do I start my circle? Well, yet again, you're going to use that alternative right-hand rule where your fingers will curl in the direction for your magnetic field. So that's the one that we're going to use in this problem, which we're going to cover next to give the example for Ampere's law. Okay? So what's our example? Well, we want to calculate the magnetic field at some distance r away from the center of a wire, a big fat wire, let's say for our purposes here. And that wire is carrying a steady current I, okay? And we're going to assume that this current's been on for a nice long time, it's uniform, and it's uniformly distributed throughout the cross-section of the wire. Now, we want to know what the magnetic field is at two different points. One point is inside the wire, where little r is less than big R. Big R here is the radius of our wire, and little r is going to be where we want to know our magnetic field at. Okay, so it's going to be the distance from the center of our wire to the point in question where we wish to know the magnetic field. So one point inside the wire, little r, is less than big R, and one point outside the wire, big R, is less than little r. Okay, so that's where we want to know our magnetic field. So let's do outside of the wire first. Okay, outside of the wire, little r is greater than big R. So that means that if we draw an Amperian loop at the point in question that completely circles the wire, now to exploit symmetry, we want to make sure that our Amperian loop is concentric with the wire's cross-sectional circle, okay? So we want the center of the wire and the center of our Amperian loop along that axis to be the same point, okay? So that's as it's drawn here in the figure. what we're going to show is that here, right, we're going to show here I is the direction of the current. So if you point your thumb in the direction of the current, your fingers will naturally curl in a counterclockwise direction around that wire. So that's the direction we're going to do our line integral in for our magnetic field. Okay, that's the direction. You can see here that ds at the point is shown here in kind of the lower right hand corner of our Amperian loop circle. ds is pointing so that it goes counterclockwise, all right, at that point. Okay, so here we have B dot ds. Now, we know from our previous work with the Biot-Savart law that the magnetic field is going to be all along our Amperian loop the same value, okay? And it's going to be the same value because we're calculating the magnetic field at the same distance from the center of our wire, okay? So as long as we're the same distance from the center of our wire, our magnetic field magnitude should not change. Now the direction will change, it makes the circle, but the magnitude of the magnetic field only depends on our distance from the center of that wire. So once we calculate our magnitude, we can pull our magnitude out as a constant, okay? Now, this is a vector dot product, B dot ds. You can see that our magnetic field encircles the wire, okay? So it points tangent to that circle. So does ds. So at all points along our line integral, B is parallel to ds. So when you take the magnitude of a vector dot product, you're doing vector 1 magnitude times vector 2 magnitude times the cosine of the angle in between vector 1 and vector 2. So here we would have magnitude-wise B ds cosine theta. But because B and ds are parallel, cosine of theta is cosine of 0, which is 1, okay? So our magnitude is 1 there for our cosine, right? Now another thing here, ds is our little line element, and that's going to be, because we're walking in a circle, r d theta, okay? So we can pull B outside, it's a constant, and then we're integrating in a closed loop r d theta from 0 to 2 pi, okay? Now, because r does not change here, we can also pull it out of that integral if we'd like, and then we're just integrating d theta from 0 to 2 pi. So when we perform this integral, we get b times 2 pi r, right? And that's what's equal to for the closed loop b dot ds. Now, Ampere's law says that this line integral is equal to mu naught times the current enclosed by our Amperian loop. Because we're outside of the wire, the amount of current that's enclosed by this Amperian loop is all of it, or I. So we can say that B times 2 pi r is equal to mu naught I. And then we can solve for our magnetic field B, and it's mu naught I over 2 pi r. Okay? If you don't understand, make sure to pause the video and stare at it until you get it. Moving on. Now let's examine the case where we're inside the wire, okay? Now, you can imagine that if you're inside the wire, your magnetic field is still going to make circles, right? It's just that maybe the magnitude of the magnetic field inside the wire will not be as large as it would be right at the surface, for example, because you're not enclosing all the current. But you would still have a magnetic field that's making little circles inside of your wire here. So if you look at position 2 here, that's the point where we're talking about now, when we're inside the wire, r less than big R, okay? And so the magnetic field would point in the direction counterclockwise around this little dashed blue line for the inside of the wire there, okay? Since, yet again, ds and B point in the same direction at all points, and since we have our Amperian loop centered at the center of the long axis of our wire, okay, we can pull that magnetic field strength out, B. Our cosine of the angle would still go to 1, and then we're just still integrating ds, which is r d theta, from 0 to 2 pi. And so our integral, our value of our integral, is no different than it would be in the previous case. So we end up with b times 2 pi r for the value of our line integral. All right? Pause the video and think about it if that doesn't make sense to you. Now, this is going to equal times 2 mu naught times I enclosed, where I enclosed would be the amount of current enclosed by that Amperian loop. Now, in this case, we are not enclosing all of the current. We're only enclosing a fraction of the current. So I'm going to call the amount of current that we're enclosing here I prime. Now, how much current I prime would we be enclosing? We've already said that the current is uniform throughout this wire. So if it's uniform and distributed all throughout the wire, then the amount of current that we're enclosing would be equal or proportional to the amount of area that we're enclosing. So how much area are we enclosing? Well, we're enclosing pi times little r squared. That's the area of the circle that we're enclosing. But the total current is enclosed by pi big R squared. So if we take a ratio of the enclosed areas and then multiply that times the total current, we should get the amount of current that we're actually enclosing. So here I prime would be equal to the total current I times pi little r squared over pi big R squared. All right? Now the pi's cancel out, and so what we could do is now plug this back in to our expression up here, mu naught I prime, would then be equal to mu naught I times little r squared over big R squared. Okay, we're done. We've applied Ampere's law. Now all that remains is to solve for our magnetic field strength B. When we do that, we end up with B is equal to mu naught I little r over 2 pi big R squared. So you can see that the magnetic field would grow in strength when you're inside of the wire until it reaches the surface of the wire. Let's plot this. Inside the wire, the field's proportional to R inside the wire, right? So it makes a straight line. Then once it reaches little r equal to big R, once it reaches the surface of the wire and you start to move away, then it starts to fall off like 1 upon R. Okay? So that's what we've got. Next, let's talk about another really common example that gets used for Ampere's law, and that's the magnetic field of a solenoid. So remember, a solenoid is a long wire that's wrapped around a cylinder, forming a helix, okay? When you do this, you get a nice uniform magnetic field inside the solenoid. And outside the solenoid, you have a pretty weak magnetic field. So I'm going to call this the interior of the solenoid when it's inside the turns, and the exterior when it's outside the turns. So it gives you a nice, uniform, straight magnetic field inside. The field lines in the interior are nearly parallel to each other, and they're uniformly distributed, and they're close together. And this indicates that the magnetic field inside the solenoid, in the interior of the solenoid, is strong and almost uniform. Now, the more closely you wrap those turns, and the more turns that you have per unit length, the stronger the magnetic field and the more uniform the magnetic field inside the solenoid gets. Eventually you get something that looks a lot like a bar magnet, okay? Now, if you increase the length of the solenoid, then the interior field becomes more and more uniform, and the exterior field becomes weaker and weaker. Eventually you approach the characteristics of what we call an ideal solenoid. So this is when the turns are super closely spaced, and the length is much larger than the radius, okay? So then you get the scenario that's shown here. Let me explain this drawing a little bit. Right here, the little circles with the purple dots and X's on them, those represent the direction of the current, okay? So this is like if you take a slice through your solenoid, these circles with the dots coming out of them are the wires, right? And at that point, the current is coming out of the screen at you in that slice. On the other side, with the X's, the current is going into, right? So if you looked top down on your solenoid, the current would be going counterclockwise if you look top down. But this is a slice through, so it's coming out of the screen on the left-hand side and going into the screen on the right-hand side. If that's the case, then the magnetic field for an ideal solenoid would be pointing straight up, okay? Straight up. You can realize this if you think about what would happen with just one loop. Remember, with just one loop, we had a magnetic field that encircled the loop. And so if you curled your fingers in the direction of the current, then the magnetic field at the center of the loop would be pointing up, and then it would come around and circle around the loop and come back down. Well, here basically you have a lot of loops that are stacked on top of one another, right? So what that means is that outside the solenoid, it's really, really super weak. But inside the solenoid, you're looking down on it, it's coming up at you, and it's strong and it's uniform. Okay? So it's a bunch of stacked loops, basically. So here we have our magnetic field, and it's more or less straight, more or less uniform, and very strong. Okay? Now let's apply Ampere's law to find out what the expression for the magnetic field inside on the interior of a solenoid is. What Amperian loop would we choose? Well, based upon the symmetry of the situation in the magnetic field, what most folks do is choose an Amperian loop that's a rectangle. Okay? Now, this rectangle is shown here in dashed blue lines in the figure. It has a length L and a width W. So here what we would do is we would walk when we're inside the solenoid in the direction of the magnetic field. And then we would turn right and walk along W to the right, and then we would turn down and walk along L downward, and then we would turn and we would walk along path 4 here, going to the left. Okay? So that's what we're going to do when we talk about our solenoid, okay? To find the magnetic field on the inside. All right, so if we do that, then what we can see is applying Ampere's law that we end up with B dot ds. Let's look at path 1 here. In path 1, if we apply and do our Amperian loop in a piecewise continuous fashion, then B dot dl, B and our ds are pointing in the same direction here. So as we walk along path 1, our cosine theta term would go to 1. The magnitude of our magnetic field is B, and then the integral of ds would give us L. So as we walk along that point, we get B times L. Now we turn right and walk along path 2. Well, in that case, our ds and our magnetic field go to 0. B dot ds goes to 0. And that's because the angle, when we're inside the solenoid, the angle between B and ds is 90 degrees. And the cosine of 90 degrees is 0. So when we're inside, right, then we get B dot ds is 0 because they're perpendicular to one another. Now, once we get outside, the magnetic field goes to 0. And so at that point, it's 0 anyway. Now, when we start to walk down along path 3 along L, then B dot ds is still 0, and that's because the magnetic field is 0 outside of the solenoid. So B dot ds is 0 trivially because B is 0. When we walk along path 4, B dot ds is 0 because both it's 0 when you're outside the solenoid, and then when you get inside, they're perpendicular to one another. So the cosine term would give you cosine of 90 degrees, which is 0. So for the entire Amperian loop, the only segment which contributes something that's non-zero is BL. And so that's the evaluation of our Amperian loop, BL. Okay? Now, we have to set this equal to mu naught times I enclosed. So what is our total enclosed current? Okay? So our total enclosed current would be the current through each loop, which we'll call I, times the number of turns, right? And the number of turns would be the number of turns that you get in whatever length you've got there. So I guess, for example, here we'd have 1, 2, 3, 4, 5, 6 turns enclosed in our little Amperian loop. So it would be mu naught times 6 times I, because we're enclosing 6 turns there. All right? But now let's generalize a little bit. When we solve for our magnetic field, we have BL is equal to mu naught times Ni, where big N is the number of turns that we're enclosing with our loop. When we solve for B, we get mu naught times N over L times I. Now here, N over L is the number of turns per unit length, okay? So oftentimes when we speak of solenoids, we just go ahead and call that little n, the number of turns per unit length. And when you wrap your solenoid, you try to keep the number of turns per unit length a constant so that you can easily figure out what the magnetic field should be like on the inside of your solenoid. Okay? Now this was for an ideal solenoid, which would be infinitely long, But this expression would be valid for a regular solenoid as long as you stick to the region near the center. When you get near the ends, you've got fringing effects, and your magnetic field strength outside the solenoid gets stronger, and so you can't really count on this expression always to work. All right, I hope that helps, and if you have any questions, let me know, and I'll see you in class or in Zoom.